All right, how's it going, guys? Back for another recitation. Today we got recitation number 8, and this is shifting gears quite a bit. It's actually kind of going back to outcome 1, if you recall, where we do a lot of dimensional analysis, stuff like that. So this will be outcome 4, where we just take dimensional analysis a step further and start to like non-dimensionalize numbers and equations and things like that. So I'm sure you've been going over this quite a bit in class, and it's really not too bad. I say, this stuff is like free money on an exam. It's really pretty easy, pretty straightforward. But anyway, so we've got 2 problems. This first one says it's all about pi groups and dynamic similarity, okay? So for this one, we've got the power produced by a wind turbine depends on its angular velocity, omega, diameter, d, number of blades, b, blade chord width, c, as well as the air density, rho, and wind velocity, v. And the chord for some, like, blade or wing or something, that's just the distance from the trailing edge to the leading edge, if you didn't know that. But all right, so for part A, I want to show that the dimensionless power coefficient Cp is equal to P over rho d squared v cubed, where P is the power, and it's functionally dependent on the advance ratio V over omega d, the aspect ratio D over C, and the number of blades. So for this one, okay. So you can do this a couple of ways. If you really want to see the full explicit way of going about doing like the pi group stuff, go check out the key I'm going to post. They show you how to like pick your repeating parameters and do all that stuff. Raise them to the powers, right, and get the MLs and Ts to go away. I don't think it's really that necessary to go and show that in this. We'd be here all day. It's kind of a drawn out process. And if you really, if you don't want to reverse engineer it, right, if you want to find out which parameters they're repeating and whatnot, let's go look at the pi groups they give you, right? See which ones they're repeating. We've got a rho d and a v, we've got a v and a d, we've got a d. So they're probably repeating the rho, d, and v, right? But anyway, so for this, I think it's sufficient just to show that these pi groups are all dimensionless, and therefore they are all functions of each other in terms of this problem. So for any of these problems, it's best just to write out the dimensions of all of the variables and parameters of the problem. So let's go ahead and do that. I'll just do it down here. So we got power. And this is another reason why I said if you talk to me in person, it's good to save the cheat sheets from previous exams, because I can't remember the MLT version of power off the top of my head. So I go and look it up and write it on my cheat sheet. So we got ml squared over t cubed for power, angular velocity omega. I always remember that as it's something per second, 1 cycle per second, right? Like radians per second, 1 radian per second, right? Then we've got diameter. It's just length, obviously. Number of blades, b. This is dimensional. This is just a number, right? It's like 4, right? So I'll just write that as 1. The dimension is just 1 unity. It's dimensionless. Blade chord, right? That's again just another length. Air density, we know air density. And lastly, wind velocity, v. That's just L over T. All right, so now let's show that these pi groups are dimensionless, right? Let's just show that these are dimensionless. So let's go with Cp equals P over rho d squared v cubed. And this is, I'm literally just going to math it out, just super basic algebra. That's what I love about these, it's just really basic algebra. And then we've got cool. Let's now literally just go and cancel out all the units. So we got L's cancel, M's cancel. We're just left with equals 1. Check. Cool. All right, so now let's go to the other one, V over omega d, the advance ratio. Again, this is L over T, 1 over L. Cancel everything. Boom. Yep, it's dimensionless. The other one, hopefully you can see that this one's dimensionless. D over C, length, 1 over length. Not bad. Let's see, yeah, 1 blah equals 1, and check. And then B, of course. Last one is B. That's already dimensionless. So boom. All right, so they're all dimensionless, right? And so therefore, because they're all dimensionless and they are all made dimensionless via the same parameters and the same problem, okay, you can say that they're functionally dependent upon one another. If you go and like plot them against each other, right, you can find some functional relationship that relates them all to each other. You're not going to actually have to find what that relationship is in this class, but just know like that's what we mean by that. So I think that's sufficient for part A, right? Like I said, the key will go and show you very explicitly how to do it like from scratch, but whatever. Anyway, all right, so for part B, it turns out that the number of blades and advanced ratio can be defined in one similarity variable called the solidarity ratio, given by BC over D. Thus, CP is a function of V over omega D and BC over D. Strictly speaking, right, since everything's non-dimensional, you can combine them as much as you want, really. It's just convention that we choose to pick certain non-dimensional numbers in various ways because they tell us certain things about the flow, right? Like the Reynolds number, it tells us a lot about turbulence and things like that. So we tend to group them in certain ways, but strictly speaking, there's no real reason you need them in one form or the other, as long as it's dimensionless, right? That's totally fine. But anyway, so for this part, we are going to assume you're testing a model of wind turbine. The full-scale wind turbine has 3 blades, a diameter of 40 meters, and an average chord equal to 2 meters. The model has 2 blades and is limited to a diameter of 2 meters. What does the model blade chord have to be for the test to be dynamically like full-scale operating conditions? All right, so for this part, we're going to be matching these pi groups and making this scenario dynamically similar, right? And I'll just kind of draw a line to separate this. So we need to match these pi groups, okay? We need to match these numbers to make the dynamics of the problem from the prototype to the model similar, right? So we can go about testing this model and make sure that the physics of it will align correctly with the full-scale model. So we're given full-scale wind turbine. So B. So the full-scale thing is always called the prototype, right? So 3 blades, diameter 40 meters, and then chord, it's 2 meters. And we're also given B model equals 2, D model equals 2 again. And we're trying to find that, right? Trying to find the chord. So literally, which pi group has B, C's, and D's? Well, we've got one that has B, C's, and D's right there. So let's do that. So we're going to have BC over D prototype equal to BC over D model. So we've got 3 times 2 over 40 equals 2 times CM, what we're trying to find, over 2. Literally just super basic, go solve for CM. CM should be 15 centimeters, 0.15 meters. Cool. So for these ratios to be the same, right, and for the whole situation to be dynamically similar and match this BC over D number, you'd need the chord to be 15 centimeters, right? Or else the proportions would be all off and the experiment wouldn't match the physics of what's going on in the real world. Basically, that's what that means. All right, now the next one, model test conditions are in a wind of 40 meters per second, and the model rotates at 500 radians per second. The full-scale wind turbine operates in a 12 meter per second wind. What should the angular velocity be for the 2 wind turbines to have dynamic similarity? All right, so now we're going to be matching this one, right? We're given omegas and velocities, so let's go match that one. So literally same thing as before, but we've got V model is equal to 40. And omega model is 500. And then we've got V prototype is 12. All right, trying to find omega prototype. All right, so again, literally do the same exact thing. We've got V over omega D So we have 12 over, don't know, times 40. It's equal to, what we got, 40 over 500 times 2. Right, and so again, just solve for it. Really, really easy. So we have omega p, 7.5 radians per second. And think about units, you really don't need to do any unit conversion for this stuff, as long as you are consistent with your units across the numbers that you are comparing, right? So both of these velocities have to be meters per second. Both of these omegas have to be in radians per second, diameter, meters, whatever. Just know whatever, as long as you're consistent with your units, right? When you're solving for the other variable on the other side, it will just spit out the same units as the opposite variable, right? So omega m was radians per second, so omega p is also radians per second. That's pretty much it, right? All right, so it's pretty much all about that. All right, now part C, both the model and the full-scale turbine are operated in air, so density is going to be the same. If the power produced by the model wind turbine is 8 kilowatts, what is the power produced by the full-scale wind turbine operating as determined part B? So now we're just going to match this last one, the power coefficient. So lastly, we've got right, power of the model is 8 kilowatts. All right, so let's go match these numbers. So we've got P prototype over rho times, we've got diameter squared, so 40 squared, right, times velocity cubed, so 12 cubed. It's equal to 8 kilowatts on the other side, and then same density times 2 squared times 40 cubed. All right, so densities cancel, we don't care about those. Now go solve for P. It should be 86.4 kilowatts. Cool. All right, which makes sense, right? A lot bigger wind turbine, a lot larger power. And then the opposite's true over here, right? It is a much larger turbine, so it doesn't need to be moving quite as fast to get the same dynamic similarity stuff going, right? That brings up another point. A lot of times you do this in experiments too, to even see if like testing things are feasible, right? You know, say your power company that you're making the prototype for needs their big giant wind turbine to go like 20 radians per second for some reason. Well, if you go and try and solve back and say, okay, well, I've got this little small wind turbine at my lab, can I use it to model the situation? Well, if you go back and find that you need the thing to be ripping out like 3,000 radians per second, maybe you go, okay, maybe I can't test this in my lab, right? Maybe I either have to build something new or go outsource it to someone else or try and match a different number, you know, stuff like that. So you do this math beforehand so you don't go and build the damn thing and realize it doesn't work, right? And you can't match the physics of the situation that you need to model. So you have to go and try something new. But yeah, that's really all that is. It's really not bad. It's pretty basic algebra. It's, you know, very much an extension of outcome 1. So yeah, pi groups, stuff like that. It's a good time. It's not too bad. And for the next problem, for this one, we're non-dimensionalizing this partial differential equation, okay? And so here we've got the wave equation is immensely important in many areas of engineering and physics as it governs the propagation of many different types of commonly seen waves. Strictly speaking, it is a second-order linear partial differential equation. Actually, the fact that it's linear, right? Like when you, so, you know, this governs waves and whatnot. So, like, you know, you've seen two sine waves, like when you add them together, right? They make like a big spike. That's because they're linear combinations of each other. So linearization is very important in engineering. Should you take MAE 502 here at ASU, you will learn how to solve it by hand, which really isn't too bad. I did it. Actually, I wrote this problem. It's not too bad. It's kind of a lot of legwork, but it's interesting. For now, consider the one-dimensional version of the wave equation, which can be written like that. Partial squared u over partial t squared equals c squared, partial squared u over partial x squared, where c represents the propagation speed of the wave. Recast this equation into its non-dimensional form. Additionally, u represents the wave's actual displacement, amplitude, t is the time variable, and x is the location variable. All right, so when you're non-dimensionalizing PDEs, it's really important to realize what is a variable and what is a parameter. So variables obviously are the things that are varying with the problem. So what's varying? Let's write our variables down. Obviously, u is a variable. That's literally like if you were to solve this, you would solve for like u of xt equals, some equation, blah, blah, blah. So u, and that's, it's an amplitude, so it's some length, right? The other one is x, right? The location variable. That's, again, just a length. And then t is time. Cool. So now for our parameters, okay? Parameters are things that are like constants inside the problem. All right? And in our case, the wave speed, c, propagation speed, we'll call that a constant. And that's a speed, L over t. And also, you also have to think about this problem like more physically, okay? So let's say we actually have some actual situation going on here where we've got this wave, right? Maybe a little something like that, whatever. And we want to find, this amplitude right here, u of xt, okay? Well, if we got this physical situation here, this whole problem is going to be governed by some like real length and some real time, right? If we're trying to find, the amplitude of something with respect to some position and some time, we need something to like compare it to, okay? So we call that, we've got some characteristic length scale, right? So let's say this wave travels 10 meters down and then reflects and travels another 10 meters back, right? That's like our characteristic length scale, okay? And with that, if it varies with time too, we have some overall big time scale, and we'll call that big T, right? Some time big T, all right? That's our characteristic time length. So let's say it takes 20 seconds to go down and back, right? That, and then it repeats itself over and over again. That's our characteristic time scale. So we also have L, and that's just a length, and then big T and some time, right? And you can go and put like knots on here, you can pick whatever kind of variable you want for it, doesn't really matter. But all right, so now we're ready to roll. So now we're going to make our reference variables. These are typically denoted with like stars on them. So we're going to make some non-dimensional reference variable u star, which is equal to the original u non-dimensionalized by one of these parameters, all right? And we need to do this for each variable. So how do I non-dimensionalize some length? Well, how about, let's use another length. Boom, done. Same thing, let's go x star is equal to x over, again, non-dimensionalize it with one of these. Let's just use length again. Obviously, it's the only thing that works. And then t star. Right? But in this form, they're not really that useful to us, right? We want to be able to plug them back into the PDE. So let's go and solve them for our original variables. So u literally equals u star times L. X equals x star times L. And t is equal to t star times big T, okay? Now we can plug these back into the PDE. All right, so we go partial squared, and what's u? U is u star L over partial, we've got t star big T squared is equal to c squared. And we don't need to do anything with that right now, that's fine. All right, and so now, what's really important for this is we need to realize what these partial derivatives are actually doing, okay? First off, derivatives and all that only apply to variables, okay? They only do anything to variables when when you're taking the derivative of a constant, right? You can just pull the constant out. So same thing in this case. We want to try and pull out these constants, these L's and these T's, right? Because they don't do anything inside of these partial derivatives. So the other thing that's important is we need to look at these squares, right? What these squares are being applied to. On top here, in both cases, right, the square is being applied to the differential operator, right? The partial squared. But on the bottom, the square is being applied to the parentheses, right? So these parentheses are getting squared down here, but not up here. So let's do that. Let's take out those constants. So on the left-hand side, we'll have an L over t squared from the bottom, right? L t squared, and times partial squared u star over partial t star squared. And similar thing over here, right? We've got a c squared, and up top we have an L over L squared, partial squared u star over partial x star squared. Okay, and so now let's look, like after every step you should stop and say, hey, how close am I to actually non-dimensionalizing this thing? So let's look at it. So our partial derivatives, right, our partial or squared, whatever you want to call them, second order partial derivatives, these are all fine. These are now non-dimensionalized, these individual terms, because we had defined these u stars and x stars and t stars as non-dimensional variables, right? So inside the partial derivative, they are non-dimensional, so that's cool. But obviously we have L's and T's and all this stuff floating around. These obviously are not non-dimensional. So after this point, just kind of start multiplying, dividing stuff over and seeing what works. You know, like I said, after every step, just kind of check if it's non-dimensional or not. But for now, I'm going to multiply the t squared and divide the L over. So let's do that. And I'll bring it like down here. So we've got a partial squared u star over partial t star squared equals c squared. And I'm multiplying the t squared over, so we're going to have a t squared up top, and then dividing the L over, so those L's cancel. So we'll have an L squared on the bottom, and partial squared u star, partial x star squared. All right, and now it's like, okay, have we completed our job? Well, it's like, so we already said that's non-dimensional, that's non-dimensional. Now let's look here, right? C is some velocity, so L over t, right? So c squared is L squared over t squared, and then you're multiplying it by a t squared over L squared. So hey, boom, actually we are done. Cool. So technically speaking, you can totally stop right here, right? And this parameter right here, this would be like a scaling factor, right? This would turn into, you know, like when you go and do these example problems and stuff for like a PDE class, right? All the time, they'll have you just have the scaling factor be like 7 sitting out front. It'll just affect the shape of the wave, right? And how quickly it propagates. But it's non-dimensional, so that's good. That's cool. Alternatively, though, on the t, I mentioned, you know, a way, if you want to get it into the totally like canonical form where there's no extra parameters laying around, if you very intentionally pick your L and T such that C is defined in terms of L and T, you can go and cancel that out, but it's not super necessary. In fact, when I was doing it like in the in-person recitations, it was kind of confusing people, so I'm not even going to do it on here. It's on the key that I'm going to post, but yeah, this is how you do this. This is a really basic one. Hopefully, you know, they should go over a tougher one in class, or, you know, look up how to do this stuff. It's all over the internet. But this is just a real nice basic one. Shows you how to do it. Shows you the basic steps. It's really not too bad. But yeah, once you get everything non-dimensional, right, all the terms cancel and whatnot, your job is pretty much done. So, you know, you can make this look as fancy as you want or not. All right, it's really all the same. But yeah, this stuff's not too terrible. This is one of the easier things I would say to do in this class. If you're super confused, of course, drop a comment in this video or shoot me an email if you have my email. But that's pretty much it. All right, thanks, guys.